The atom, your note says atomic theory and the atom. We're going to talk about both of those. There are 3 laws that we need to be concerned with for describing the behavior of chemical reactions. The first one, which is the backbone of chemistry, is the law of conservation of mass. And it states that mass cannot be created or destroyed during ordinary chemical reactions or during physical changes. Okay? That's the backbone of chemistry. It's why we balance equations. It's why we can figure out if I start with 5 grams of something, how much can I make? It's because in an ordinary chemical reaction, the mass is not created or destroyed. Okay, so I can account for that. And by ordinary chemical reactions, I am referring to anything but a nuclear reaction. Nuclear reactions are not considered to be ordinary because they involve the nucleus, whereas all the other ones don't. And in a nuclear reaction, you actually convert some of the mass to energy. So there actually is a small amount of mass loss, but it's being converted to energy, which is why they're such powerful reactions. The second one is the law of definite proportions. We talked about that in chapter 1, but basically it's stating that chemical compounds contain the same fixed ratio regardless of how much of the compound or where I got the compound. So for instance, the sodium chloride, which is table salt, is a little over 39% sodium by mass and a little over 60.5% by mass of chlorine all the time, every day, twice on Sunday. Okay? No matter if I have 2 grams, 20 grams, 200,000 grams, 2 million, or 2 bazillion, which is not really a letter, not really a number, but we just made it up. You get the point. It is? Yeah, true. It has letters in it, though. Okay, so that's the law of definite proportions. The law of multiple proportions we also talked about first chapter, and that states that 2 or more compounds composed of the 2 elements, although they can form different compounds, they still do so in that fixed ratio. For instance, carbon and oxygen can form carbon monoxide, or they can form carbon dioxide. That's just one example. There's like carbon and hydrogen can form who knows how many compounds because they share electrons, so they can do all kinds of crazy things. That brings us to atomic theory. John Dalton, I think someone got that for the project. John Dalton was an English teacher, get that proposed an explanation that encompassed all 3 of the laws and proposed what's called Dalton's atomic theory. And it has 5 postulates, or components. It's just a fancy word for components. The first one is that all matter is composed of extremely small particles called atoms. He said, number 2, that atoms of the same element are exactly the same in size, mass, and other properties, and that atoms of different elements differ in size, mass, and other properties. Well, the second part is like a duh. Okay? Number 3, he said that atoms cannot be subdivided, created, or destroyed. 4, atoms of different elements combine in simple whole number ratios to form compounds. In other words, I can't have half of an atom join with 3/4 of another atom. It's whole atoms that are joining up together. Okay? And then lastly, when you do have a chemical reaction, the atoms that are involved in the compounds are simply combining, separating, or rearranging. They're not being destroyed. They're not being created. They're just rearranging themselves. Okay? There are 2 of those that are no longer true, or that we have found to be not necessarily they're no longer true. First one is something called isotopes, which are atoms of the same element that have different number of neutrons. And so that different number of neutrons gives them a different mass. Okay? So I have, let's say, oxygen. There are 3 isotopes of oxygen. One has a mass of 16, one has a mass of 17, one has a mass of 18. Okay? They're all oxygen. They still have the same properties. They just have different masses. Okay? And then the second thing that is no longer held to be true is he had said that atoms could not be subdivided, and we now know that they can because we have protons, neutrons, and electrons. So they can be subdivided. Okay, so you can have an electron, you can have a proton, you can have a neutron. Okay, in order for them to retain their properties, though, they have to be a whole atom. Because if it lost an electron, it's going to behave differently. If it loses a proton, it's a totally different element. Because a proton, yeah. If it loses a crouton, it's just a sad salad. I have not had lunch.
I like salad. Sounds good right now.
Yeah. Okay. So how are we doing? Are we still writing on that page?
Yeah.
Okay.
Now I really want a salad.
So isotopes are all the same element.
Yes, they just have different number of neutrons, and that gives them a different mass. So they're not completely identical, which is what Dalton said, because they have different masses.
But they all have like the same like properties.
Yes, like oxygen 16 is going to have the same properties as oxygen 17 and oxygen 18.
How are they made then? Like,
How are they made? God made them. I mean, they're
they
here.
Just exist?
They just exist,
Okay,
yeah.
It's not like
So that's a deeper philosophical discussion
That is not meant for.
that is above my pay grade.
Wait, so
If you ask me, I'm just going to say God made them and they're here. Other people might say other things. That's just what I'm going to say. Doesn't mean you have to say it. Doesn't mean you have to believe it. I'm just saying that's above my pay grade. I just assumed they were here. Yeah. So, okay. I'm going to. You have a question?
Yes.
Okay.
So this is probably a dumb question, but
I'm supposed to say there's no such thing as
but
dumb
it
questions.
could be a dumb question. So it's atom, cell. Oh, no, atom like atom. So there's a compound of oxygen, right?
Okay, so you're wanting to know, like in biology, it's cell.
Like let's say there's water, but in water there's an
So atom is the simplest form, and then which is an element. Then you can put atoms together to get compounds. Then you can put compounds together to get mixtures. Then you can put mixtures together to get all kinds of things.
The atoms don't. Otherwise, cells would be a little.
But cells are made up of atoms.
Yeah, but then cells.
Cells are made up of atoms. So atoms is so in biology they tell you that cells are the building blocks of life, but I will tell you that atoms are the building blocks of everything except for one thing. No, they're building up your life.
Dark matter.
Light.
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 What's light made up of?
Well, wait till chapter 4. Stay tuned. Same bat channel. Chapter 4.
so isotopes.
Okay. The structure. Yes. You still have a question?
Yes. So isotopes are atoms, or just a special form of them?
They're not a special form. They just have different number of neutrons. Every element. Every element has isotopes. It's just they're naturally occurring. They have different. Let's go further into the lesson, and maybe it'll make more sense why they have different number of neutrons. They just do.
Okay, so like there's the element, and then like there are isotopes of that element that have different numbers of
Neutrons.
Okay, that makes sense.
Okay, so the structure of the atom, early models. The first person to ever come up with anything about the atom was a Greek philosopher by the name of Democritus. In around 400 BC, he decided, or he said, remember these are philosophers, so they're just sitting around thinking about stuff, and he says, I think that all the matter in the world is composed of tiny little particles that he called atomos, which was the Greek word for indivisible. However, he was a student of Aristotle, also a Greek philosopher who just sat around thinking about stuff. And regardless of whether they had information to back this stuff up they were thinking of, and he disagreed with Democritus. And because he was the teacher and Democritus was the student, for about almost 2,000 years before anybody revisited the idea that we had these atoms. Okay? Actually, Aristotle believed that all of the matter in the world was made up of 4 elements: earth, water, air, and fire. Those 4. Yeah. He was a little wrong. But for 2,000 years almost, they considered him right. Okay? The first person to discover any parts of the atom was a man by the name of J.J. Thompson, and he discovered the electron through the cathode ray tube. In your homework over the weekend, they talked about him and what he did. But he was able to discover that there was an electron. Of course, it's electrically negative, and we know that atoms are positive. So he proposed the plum pudding model, which was a basis to predict that there was something like protons out there. Because if I have a negative out there and my particle is overall has a neutral charge, something's got to be positive to cancel it out. And he also proposed that because electrons have such a small mass, something else in there needed to account for the mass of these atoms. Then came along Rutherford, who was a student of Thompson, and he discovered the nucleus using the gold foil experiment, also in your homework from the weekend, which he bombarded the gold foil with positive alpha particles, and he expected them all to pass straight through. Most of them did, but some of them did not, and they were deflected back, and they were actually deflected back with a very large amount of force. And so he concluded those positive alpha particles were hitting something else positive and pushing them back out or deflecting them back. And so that's how the nucleus was discovered, is there must be something very small and dense in somewhere in that atom because my positive particles are being kicked back out at me. The vast majority of an atom is empty space, which is why the vast majority of the alpha particles passed through the gold foil, but some were deflected. So, the atom is made up of two regions we now know, and that is the nucleus and the electron cloud. Okay? The nucleus. Okay? The nucleus and the electron cloud. Okay? So, let's talk about protons first. They are positively charged. They are located in the nucleus. And the number of protons does not vary in an element when we're doing ordinary chemical reactions. So the amount of protons stays the same. We identify elements by their protons, okay, however many they have. The symbol for the proton is a P plus sign because it's a +1 charge, and we define the mass as 1 atomic mass unit. Technically, it is 1.6 times 10 to the negative 24 grams, okay, which is a very difficult number to utilize in the calculator.
You need to know that.
So you need to know roughly what the mass is.
But we don't need to know the grams.
Do we need to write down 1.7?
Is it in your notes?
No.
Okay. The basic thing you're going to need to know is that protons and neutrons weigh essentially the same, and an electron is much, much lighter. Okay. Because we give it a mass of 1 AMU, which is an atomic mass unit, because that's easier to work with than 1.67 times 10 to the negative 24 grams. Okay. Neutrons are high energy, neutrally charged, located in the nucleus. The number of neutrons can change, and it does. That's what we have isotopes. Neutrons stabilize the nucleus by what are called nuclear forces. Makes sense, it's a force in the nucleus that stabilizes an element or nucleus. So they're called nuclear forces. They are short range. They can be proton to proton, proton to neutron, or neutron to neutron forces. But they're essentially what's holding that nucleus together in the middle of the atom. Without nuclear forces, everything would just be blob, be a big blob. Wouldn't hold it together. Okay?
But
Also,
if it's proton to proton, then why is it in the nuclear?
because it's still in the nucleus, right?
So that could go with protons.
It would go with what's holding the nucleus together. What binds the nucleus together? Nuclear forces, which stem from either proton to neutron, or neutron to neutron. Okay? The electron is negatively charged, located in the electron cloud, and the number of electrons can change in a nuclear in a regular ordinary reaction. And they do. You'll see that when we get to bonding, it's all about the electrons. Are they gaining, losing, or sharing electrons? The atom will gain, lose, or share in order to form compounds. The protons and neutrons just kind of hang out and see what's going on. Okay? Their symbol is E with a negative sign, and the charge is a -1. And you need to know that the mass is much, 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 much lighter. Okay? So the electrons contribute pretty much nothing to the mass of an atom. So the nucleus contains most of the mass of the atom, but the electron cloud contains most of the volume of the atom. So an atom is mostly empty space. Just like this room is mostly empty space. Yeah, we got desks, yeah, we got chairs, yeah, we got people, but if you were to take all of it into account, it's mostly empty space. If you were to take into account that all the stuff that's made up of atoms are also mostly empty space, then it's really mostly empty space. That's deep. Okay? So that brings us to isotopes. We already said that that's why that one postulate of Dalton's theory was thrown out, was because we have these isotopes. They are the same number of protons, atomic number is the same, chemical properties are the same, they just have different number of neutrons, which gives them a different mass. Okay? When we talk about an isotope, we refer to it by its mass number. So a while ago I told you there was oxygen with 16, a 17, and an 18. So we would say oxygen 16. That means mass number of 16. Oxygen 17 has a mass number 17. Okay? They have the same chemical properties, just different masses. Okay? And I'm going to show you now how we would write that. There's two ways that we could write that. First way is this way, where we write the symbol right here. And the top number is the mass number, and the bottom number is the atomic number. Or we would write it like this, sodium-23. And we would say that had sodium-23. Okay? When we're referring to any kind of general term for an isotope, we call it the nuclide. So we would say the sodium-23 nuclide, or the sodium-23 isotope. Okay?
Could you go back? Thank you.
Okay, we good? The atomic number, which we call Z, is the number of protons in the nucleus. The atomic number, or the number of protons, is how we identify elements. It's how we identify elements. For those of you who have not figured out how I'm doing the date on the board, those are their atomic numbers, because that's how we identify them. So today is September 17th. Fluorine's atomic number is 9. So there's the September. The date is the 17th. Chlorine's atomic number is 17. And then calcium is 20. And argon is 18. So it's 9, 17, 20, 18. So that's, if you haven't figured that out, that's how that date is done. It's covered up right now. You have to use your periodic tables, because I have ours covered up for our element quizzes. Okay? So you will need your periodic table that I gave you, that you colored all nice and pretty. Speaking of, when is the next element quiz? Tomorrow. There you go, tomorrow. Okay. So the mass number is A, and that is the total number of protons and neutrons. So if I know the element and I know its mass number, can I figure out how many neutrons it has? I have the mass number and I know the atomic number. Can I figure out the number of neutrons?
Yes.
And how would I do that? Subtract them, yeah. Okay, so here we have 3 special cases of isotopes, and that is for hydrogen. Hydrogen is the only element that we actually name the isotopes, okay? They actually have special names. All the other ones, we just call them by their mass number. Every element has at least 2 isotopes. Some have as many as 25. Okay. Here's the special case for hydrogen, though. We have protium, which is the vast majority of hydrogen, and then we have some deuterium and some tritium. Protium, which is the most common isotope of hydrogen, is the only one that doesn't have any neutrons. There's no neutrons. Okay. 99-point-something% of hydrogen is that isotope. Okay. Deuterium has 1 neutron, and tritium has 2 neutrons. Didn't make that plural. Has anybody ever heard of heavy water? Somebody said it.
I've heard of hard and soft water.
That's different, yeah. So heavy water is water that is made with the deuterium isotope of hydrogen, so it actually has a higher mass than regular water. But
Does it taste different?
I don't know. I've never tasted it. I've just heard of it. I've never even seen it.
Can you drink it?
I would think that you could, because chemically it's the same. Chemically it's the same.
So even if it
Yeah.
has one-
And there's a small percentage of water that is probably heavy water. It's just such a very small percentage, like maybe 0.01%. I don't know. Off the top of my head, I don't remember the percentages of the isotopes. I can look it up. But I know it's a very, very small percentage.
If it's tritium, what would be that? Super heavy water?
I guess I don't. I actually have to look that up. You know what? I'm going to assign that task to you, Sean, and you find out.
If I find heavy water,
Okay? You can't find it. It has to be isolated, and yeah, you can't just go out and find it. Okay? So in order to figure these out, you can either just remember to subtract, or you can use this 8-man turn, which is atomic number equals protons and electrons, and the mass number minus the atomic number gives you neutrons. I don't technically use that. I just give that for you. I just can remember to subtract them, right? So we're going to practice with uranium-235. So I've got the protons, the neutrons, and the electrons. Okay? Uranium-235, if you look that up, its atomic number is 92. So how many protons do I have? 92. This is an electrically neutral atom, so how many electrons do I also have? 92. So in order to determine the number of neutrons, I'm going to take, and watch this. If I write it like this, which is the other way that we can write an isotope, it's like a built-in little subtraction problem right there for me. Isn't that nifty? So I would have 143 neutrons. Okay? Carbon-14, the atomic number for carbon is 6. So how many protons and electrons? 6. How many neutrons? 8. Potassium-39 has an atomic number of 19. And then 20 neutrons. And sodium-21, it's got an atomic number of 11. So that means there's 11 electrons, and how many neutrons? 12.
By the way, I found that answer you assigned me. It is called super heavy water, and it's also a radioactive form of water.
There you go.
So
Thank you.
if you drink it, it's radioactive. Like, what is that?
That means right now we have to pause. I'm trying to record a lesson, and we do not need to chase any rabbits right now. Rabbits, squirrel and rabbits, put them away for now. Put the rabbit back in the hat, put the squirrel back in the tree. Okay, I do want to talk to you about this. So, because this will show up on your worksheet today. So far I've been saying electrically neutral. Well, what if I have an ion? And we're going to learn a lot about ions as we go down the road in chemistry. But an ion is a charged atom because it's either gained or lost electrons. So let's say I had this, sodium plus, and it was sodium-23. So how would I do this now? Still 11. My protons aren't changing. Still 12. But how many electrons would there be? 10. Because I lost an electron, which are electrically negative. So then I have one more proton than I do electrons. What if I had oxygen 2 minus, and it's oxygen 18? 8 is our atomic number, so that means this is 10. But so now how many electrons would I have? 12. I would have 12 because it's a 2 negative right there. So that means I gain 2 electrons, right? Because I have 2 more electrons than I do protons now. So that's how you do it if it has a charge. Okay? So,
Yeah, it's 10.
oh, it's 10. Why did I say 12? Oh, my goodness. I should probably not lecture when I'm this hungry. I can't think. I'm so hungry. All I can think about is
Why is it 2 negative,
because it gained 2 electrons.
but not negative 2?
Oh, it doesn't matter. You can do it either way.
Oh, okay.
Technically, there is a correct way to write minus 2 or negative 2 minus, but I do not enforce that in here. I just want you to know it's negative. Okay? I just want you to know it's negative.
Can you have like 4 plus signs, or would it be 4 plus?
Oh, no, it would be 4 plus. So like aluminum, we do 3 plus. We wouldn't write all the plus signs out. That'd be redundant, yeah. So since I have written it up here, aluminum has a atomic number of 13. Let's say we're going to do 20. We're going to do 27.
So
14. And how many?
16. No, 10.
10. Yeah, 10. Now, here's what's weird. All of these have 10 electrons.
Whoa.
Is that like something you set up, or That's because it's like one.
Well, I did not do that on purpose. It works out that way because we'll find out later everybody's trying to get to a full outer shell, and by losing or gaining they get there, and so they have the same electron outer configuration, but they do not change into each other. Aluminum ion behaves very different than a sodium ion. Okay, they're just something that's called isoelectronic, meaning they have the same amount of electrons as each other. But that's like further down the road, so you can see that off in the distance. But right now it's just a mirage. Okay, that brings us to the Rutherford Bohr atomic model, and I'm sorry to bore you, but we have to go through it. I hope so. Okay. One model is Rutherford. First of all, remember he's the nucleus guy, the gold foil guy. He discovered the nucleus, which is where the protons and the neutrons are. And Bohr described electrons being in energy levels that are specific orbits around the nucleus that he called, specific paths that he called orbits. We're going to go further into that in the next chapter. But here is what they look like. He said that energy level 1 had 2 electrons, 8, 18, 32, and etc. And the number of electrons in each energy level is 2n squared. This is an overlap between this chapter and the next chapter that's coming up. And also the outer or the highest energy level is where the valence electrons are found. Okay, and those are the electrons that we care about. Honestly, they're the ones that are available to be lost, shared, or gained, so that they can form chemical compounds. Yeah, we don't care about the electrons that are underneath. We only care about the outer ones. They're trying to get their outer octet. They're trying to get to 8. Mm-hmm. Yeah, 8 is great. Yeah. So we're going to draw one Bohr model, and we're going to do neon. So first thing we do is we draw a nucleus. And what is the atomic number of neon? It's 10. So we're going to draw 10 little protons inside there. So just do 10 dots. And then we're going to draw our energy levels. So we're going to draw an energy level. And what did it say? How many can fit in the first energy level? 2. 1, 2. Let's color those in because they look like zeros. So that energy level is full, so we're going to do... Okay, how many fit in this energy level? 8. 8. And how many do we have left to put in there? 8. So put them all in there.
So is neon not very...
Neon is not very reactive. It's a noble gas, and that's why the noble gases are not reactive. They have a full outer shell.
So would the 7s be the most reactive?
The 7s and the 1s. Yeah, but that we're getting to that.
Okay.
Yeah.
So the noble gases cannot ever.
There are some compounds they can form, but they're not very many. Neon, not really, but xenon, as you get a little further down, there's more electrons, they can form some, but yeah. That's an AP Chem thing. We don't ever talk about that in here. Okay, that's where we stop. Bam, done.
So much fun.